Hi, you've come to our video on the chi-squared test for homogeneity and independence. Chi-squared is a test that lets you check if your observed value and your expected values match up for categorical variables. And you know you're doing independence or homogeneity if your data comes in a two-way table like this, which it does. But how do you know which one, homogeneity or independence, to do? Well, independence is to check if there's an association between two categorical variables. For example, adults and eating candy. But homogeneity is to check if there's homogeneity or even distribution of stuff between multiple samples. And so that's the key there. Independence will be a singular sample and homogeneity will be multiple samples. And so here it says a random sample, so we know we're doing a test of independence. We want to follow our state plan do conclude. And so we state our null hypothesis, that there is no association between each age group and the fruit eating values. So we know that that means that the proportion of 1 is equal to the proportion of 2 is equal to the third proportion, where P sub x represents the population proportion of adults in each age group. And the null hypothesis is that they're not the same. So we want to plan it out. We want to perform a chi-square test for independence. It's very important that you state independence because this is a common mistake. And if you mess this up, you'll lose points on your state as well as your plan and your concluded too. So it's very important that you don't mess this up. And you want to check your expected counts. So you check your expected counts by taking, for example, for the expected box for this value, you would take this total times this total over this one. So I have all the expected counts worked out already, and we can see that they're all over 5, so this condition is checked. And the 10% condition, which on APs you don't have to check, we will resolve here by saying that we assume that there is more than 88660 adults in this world, and so it's relatively independent sampling. And for checking the sample, we can see that it is randomly selected because the FRQ problem told us it was randomly selected. So all our conditions are met and we can go ahead with the do section. And so we want to state our equation. The test statistic, or chi-squared value, is the summation of observed minus expected squared over expected. And so you want to take your expected values chart and you just want to go add it. And when you do that, you'll get that the chi-squared value, when you sum them up, is 8.983. And the degrees of freedom, which is the number of rows minus 1 times the number of columns minus 1. So here it's 3 minus 1 times 2 minus 1 is 2. And you go to your chart and you see that your p-value is somewhere between 0.01 and 0.02. Or if you use the calculator, you'll get a more precise answer. And so you can...
So I'm going to show you how to do the same do section, but on a calculator. So the first thing we want to do is find the expected values. In order to do so, we need to plug in the observed values into a matrix. So let's go to matrix, over to edit, and choose a random one. I already plugged in the values into matrix A. I want to point out that we only want these 6 values. We do not want the totals that are given in this table. Then we'll go to stat, over to test, and all the way down to a chi-squared test. Notice how there's 2. We do not want to choose the goodness of fit test. That's an entirely different test. We click on it. We have the observed as A, expected as a random one, B in this case, hit calculate. Our chi-square value is 8.9. Our p-value is 0.011, and our df is 2.
And so you conclude, because the p-value 0.01 is less than the alpha significance level of 0.05, we can reject the null hypothesis. And this means that our sample provides strong evidence or convincing evidence that there is an association, because we did a test for independence and association, between age group consumption of fruits and vegetables. Older people were more likely to eat 5+ servings, and middle-aged people were less likely to eat it. And this part is also a commonly missed mistake. Not including context is one of the big mistakes you can lose points on for your conclude section. You want to state exactly what was more likely and what was less likely in the context of the problem. Okay, so now we've seen an independence problem. So this is a problem for homogeneity. And we can see that's a problem for homogeneity because there's multiple samples of children, and so therefore this is a homogeneity test. And if you want more practice with this, you can go to the 2011 Form B question 4 or the 2016 question 2. When you do a homogeneity test, you want to state the hypothesis in this form. There's no difference in the distribution of categorical variable here, or there is a difference in the distribution. And when you conclude, you're going to say, we have convincing evidence of a difference in the distributions of, like, for example, fruit. So a difference in the distribution of fruit-likeness.